One, two. Good day, grade 12 learners. Welcome to today's physical sciences lesson. My name is Tandiwe. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center. Today, as you know, we are going to look at chemistry again, and we will try by all means to do the revision as we just wrote our prelim exam. Remember, you can contact us on 064 748 8913 through our WhatsApp line. Now, what is going to be our today's lesson? Our today's lesson, we are going to look at electrochemical cells. We are going to start by looking at the galvanic cell. If time allows, we are also going to look at electrolytic cells. Now, as I always encourage you, I always say to you, make sure that whenever you start with a chemistry lesson, you make sure that your periodic table is with you. Now, what is it that you need to remember on the periodic table so that we can follow on today's topic? From the periodic table, we know that we have metals and non-metals. Non-metals are on the left-hand side, right-hand side of the periodic table, whereas everything that you know is on the left-hand side, which is all the metals. Now, it is very important to remember the properties of metals and the properties of non-metals as we are going to look at this topic. Because what you need to understand is that we are going to deal with electrochemical cells where we are going to look at electron transfer. Then you need to know how are each atoms or elements in the periodic table behave in terms of electron transfer. So as we know that metals, they are good conductors of electricity first of all, and they can also donate electrons. Whereas non-metals are bad conductors of electricity, and mostly they will do what? They will accept electrons, except the noble gases, which you know that they don't react with anything, so they cannot lose or accept electrons. Now, for the method that we understand that metals donate electrons, it will assist us to know why some of the metals, as we are going to look at the reactions, will lose electrons. And it will also assist us to know why are the non-metals gaining those electrons that metals are losing. And we also know the type of bonding that occurs when metals loses electrons and non-metals gaining electrons in terms of ionic bonding. Now, we are going to look at the oxidation numbers. From grade 11, we looked at oxidation numbers. We assigned oxidation numbers in different compounds and atoms. But what is important for this year is that you need to understand that the oxidation number of all elements that you see in the periodic table is 0. Therefore, if you look at magnesium SMG, you need to understand that its oxidation number is 0. What do we mean by the oxidation number being 0? We mean that that particular atom is not being charged. It hasn't lost electron. It hasn't gained an electron. Therefore, it means the electrons, the number of electrons and the number of protons in that specific atoms are neutral or are equal. Therefore, that is why we say its oxidation number is 0. However, we know that if it can happen that this magnesium, which is in group number 2, can lose electron, when it loses electron, it will become magnesium 2+. So it means now the oxidation number of magnesium has changed from 0 to 2. So what happened to the oxidation number? It means the oxidation number of magnesium has increased. This is very important to understand at the beginning, because you will see whether a substance, its oxidation number at the end of the day has increased or decreased. Because if the oxidation number changes, it shows that there was a transfer of electrons. Is either there was a gain or loss. And it is very important that we don't confuse the word transfer, because the word transfer means coming and going. So it is very important that you understand that transfer is in both ways. When a substance loses and the other one gains, there is a transfer, because the one that gains is the electrons. It means those electrons are coming from the one that has lost those electrons. So if we have oxygen as our non-metal, we know that non-metals, what they are good at is to gain electrons. Therefore, if oxygen gain an electron, we know that it will become oxygen ion, which is O2-. And when I balance it, it becomes like this. So what happens here, we already know that if it's a neutral element or a metal is 0, but it moves and goes to 2. So here, the oxidation number is increased, whereas in the second example, the oxidation number is decreased. So the increase and the decrease in oxidation numbers will also indicate the type of reaction that that specific species will undergo. Therefore, let's look at, we are not going to assign any oxidation numbers, but I think it is very important to know how do we assign oxidation numbers, because sometimes you can be asked whether was there any increase or a decrease in oxidation number. Therefore, you need to go back and see at the rules of assigning oxidation numbers. The rules of assigning oxidation numbers, they are treated in grade 11. But in grade 12, we apply the information that we got in grade 11 to know how oxidation numbers are assigned. So there are 10 rules that I've already provided to you that you can just look at in order for you to remember how oxidation numbers are assigned. However, oxidation numbers will assist us to know what type of reaction with that specific species will undergo. Now, as I said that we are going to look at a galvanic cell. We are going to look at a galvanic cell and define a galvanic cell. So as we start, we'll know that we define a galvanic cell in terms of energy conversion. So we are going to define a galvanic and an electrolytic cell in terms of energy conversion. So you need just to know in terms of a galvanic cell what type of energy conversion occurs, and also in terms of electrolytic cell what type of energy conversion occurs. And then we are going to look at oxidation and reduction, and we are going to define them in terms of electron transfer and also in terms of oxidation numbers. We'll also look at the definition of oxidizing and reducing agents in terms of reduction and oxidation. And then we'll define the anode and cathode in terms of oxidation and reduction. So these are all the definitions that we need to know before we start understanding this topic. We will also define an electrolyte. So the definitions that I've already stipulated, those are the definitions that you must know before you understand what is happening in this topic, because these are the definitions that will assist you to understand what is exactly happening in terms of the electron transfer. Then we are going to look at the cell potential in the extent of the spontaneous cell and in the way they reach equilibrium. What you need to understand is that galvanic cells are spontaneous reactions. They occur on their own. Therefore, we need to understand what happens when a galvanic cell is in function or is operating. And we also need to understand what happened, what is the relationship of the spontaneity of a cell and the cell potential until the cell reaches equilibrium, where we say the cell is flat or the battery is flat and our cell potential is 0 volts. We also need to state the qualitative relationship between the V cell and the concentration of product ions and the reactant ions. I think this one, it is very important because we will understand why the cell potential decreases immediately when the cell is in operation. So whatever that is written in red will explain what exactly happens when the cell potential starts to decrease, because they will say when the cell potential starts to decrease is because the concentration of the product ions is increasing and the concentration of the reactant ion is decreasing until equilibrium is reached. And I said to you, how do we see that the cell has reached equilibrium? Is when our voltmeter reading reaches 0 volts, and normally we say the battery is flat. We'll also talk about the movement of ions. Now we'll also talk about the movement of ions in the solution and also the direction of electrons flow in the external circuit. So the movement of ions, will always refer to it as in internal circuit, where normally they occur at our Soul bridge and also inside the electrolyte. And then the movement of electrons will be explained at the external circuit. This one is where we have a wire that conducts electricity, and we call it an external circuit. That is where our electrons will be moving. Then we will also write down the half reaction that occurs at the electrodes. Already we know that we have to define our electrodes, and we have 2 electrodes. So we need to say in which electrode will oxidation or reduction occur. And also we need to state the function of the salt bridge. We'll also look at what is it that we call a cell notation or a cell diagram, whereby we are representing a galvanic cell to say what is it that you are going to assemble as you are going to assemble your galvanic cell. What is it that you need to have for you to have a fully galvanic cell that is in operation. We'll also explain the half cell, which is hydrogen half cell, and its reference as an reference electrode. And then we're going to look at the terminals, the active electrodes and the inert electrodes. Usually we use our inert electrodes as platinum and carbon because they are non-reactive, meaning that they are not easy to react. So that is why we are using them as inert. And these ones we'll use them only when in the cases where we have a half cell that doesn't have any conductor or that doesn't have any electrode to act as a conductor. Now we are going to predict the half cell in which oxidation, I think this one is repeating, but we are now going to say which half cell will undergo oxidation and which half cell will undergo reduction. And also we are going to write the overall reaction. So there are some of the reactions that you need to write by the end of the day to say, you need to write number one, let me just stipulate them. You need to write half reactions. We are going to write half reactions. We are going to write overall cell reaction, and we are also going to write the cell notation. So all these kind of reactions, we need to know them, and we also need to be able to differentiate them so that when they say write the oxidation half cell or reduction half cell, you need to know what is the examiner expecting out of you, and you also need to know what does it mean when you say overall. So we know that overall, it means is the combination of the two half cells. So overall is one cell in operation or one cell that is full, because each half reaction, which is half reaction oxidation, half reaction reduction, when they combine together, they are going to give you one cell, which we refer to it as an overall. And then cell notation, as I said, is going to represent what is given on the cell. We are going to use the standard reduction potential table to calculate the EMF, and also using the positive value of an EMF to say that the cell is the reaction is spontaneous under standard conditions, whereby the standard conditions will be provided to us to say, what do you mean when we say the cell is operating under standard conditions? This one, I think I've already talked about it. Now, what is the energy conversion in terms of the galvanic cell? A galvanic cell changes or converts chemical energy to electrical energy. So therefore, we need to know where are these chemical energy coming from so that they can be converted to electrical energy. So that is the first thing that you need to understand about a galvanic cell. As I said, that the definition will be provided in terms of energy conversion. And then the reactions that occur are spontaneous, because it means now the cell occurs on its own. It means that there's no energy that will be added for the cell to occur. Therefore, these kind of reactions are going to be exothermic, meaning that they will be releasing energy in terms of electrical energy. Therefore, immediately when we say this reaction is exothermic, we can also integrate it and relate it to in terms of Le Chatelier's principle to see that immediately when you increase temperature in this kind of reactions, definitely if you increase the temperature, which is the information that is provided by the type of reaction that is given, if you increase the temperature, it means the forward reaction will decrease, because the increase in temperature favors the exothermic and the increase favors the exothermic. Therefore, for you to favor these kind of reactions, you definitely need to decrease the temperature, because the decrease in temperature favors exothermic. So they are exothermic reactions, and immediately when you start increasing the temperature, you are definitely not favoring the side of the product, but you are favoring the side of the reactant, and definitely your reaction will favor the reverse reaction. That is the information that is provided at the beginning. Now, redox is an acronym, as you all know, for reduction and oxidation. That is why it is divided into two: red for reduction, ox for oxidation. Now, what is this redox reaction? The redox reaction is about electron transfer, meaning that one species will lose electrons and those electrons will be gained by another species. So it means there are two species that will be reacting with each other, and therefore it means now there will be a transfer of electrons in terms of the other one losing and the other one gaining. And most of the time, the species that loses electrons are metals, because it's easy for a metal to lose electrons. However, this is not only subjected to metals. There are some of the ions that can also lose electrons, provided with the correct orientation for them to lose those electrons. And then metals, definitely, they will be used most of the time as our electrodes because they are good conductors of electricity. Now, I said we are going to define oxidation and reduction in terms of electron transfer. It is very important that you understand in which terms is the examiner looking for the definition. The examiner can say define oxidation in terms of electron transfer, or the examiner can say define oxidation in terms of oxidation number. So in terms of electron transfer, we know oxidation is the loss of electrons and reduction is the gain of electrons. And we are using oil gas or oil rig or Leo gas to assist at least to remember, because these two definitions are very close to each other, so that you don't forget which one loses and which one gain. So oxidation is loss of electron, reduction is gain of electron, or loss of electrons is oxidation, gain of electrons is reduction. These are the acronyms that we can use to assist us to just remember how do we define oxidation and reduction in terms of electron transfer. And then in terms of oxidation number, when the oxidation number of a species increases, we say that species has undergone oxidation, and when there is a decrease, we say there is a reduction. Just like the example that I provided to say when we have magnesium losing electrons and becoming Mg2 plus 2 electrons, this means is moving from 0 to 2 plus. Therefore, it means magnesium has undergone oxidation. Remember, magnesium is the one that is on the side of the reactant. Magnesium ion is the side of the product. Therefore, if I'm having oxygen, that will gain electrons and now give me O2 minus. I already know that this is reduction. Why am I saying it's reduction? Is because oxygen moved from 0 oxidation number to -2, which shows the decrease in oxidation number. So when are you going to see whether a species has lost or gained electrons? You will start from the side of the reactant, reading the reaction to the side of the product. That's where you'll see whether the oxidation number is increased or decreased. And that's where you'll draw a conclusion to say whether there was a reduction or oxidation reaction. Now, as I'm already explaining the issue of some agents will undergo oxidation and some agents will undergo reduction, meaning that some of the substances will lose electrons and some of the substances will gain electrons. Therefore, these substances that loses and gain electrons, they will react together and as part of the reactants, as the other one is losing, the other one is gaining, and we refer to them as agents. So agents, this word agent represent our reactants. So our reactants are going to be referred as agents. Reactants. Let me just write reactants. So we have oxidizing and reducing agent. As I'm saying you are an oxidizing agent, it means you are causing oxidation. Therefore, if you are an agent that is causing oxidation, definitely will not undergo oxidation. So an agent will cause the other agent or the other species to undergo oxidation, meaning that an oxidizing agent is a substance that gains electrons and is going to be the one that is being reduced. So when you are an oxidizing agent, let me just write it, oxidizing agent, okay? You cause what? You cause oxidation. Remember, you are not going to undergo oxidation, but you are causing oxidation. And when you are a reducing agent, you cause what? You cause reduction. You are not the one who's going to undergo reduction. So it means the oxidizing agent will cause the other species to undergo oxidation, and the reducing agent will cause the other species to undergo reduction. So an oxidizing agent is the one that will gain electrons and is the one that will be reduced. Why is the oxidizing agent being reduced? Because an oxidizing agent will undergo reduction. So the agents might sometimes be confusing if you don't understand them very well, because oxidizing is an action verb. So it's what you are doing. It's a doing verb. So if you are oxidizing something, you are not doing it to yourself, but you're doing it to somebody else. So it's not that because you are an oxidizing agent, you are going to undergo oxidation. It means you are causing oxidation. It means you are causing the other species to undergo oxidation. Exactly as the reducing agent. The reducing agent will do what? Will undergo oxidation. But what does it do? It causes reduction. So what you need to remember is that each agent, like oxidizing, will undergo reduction, reaction, and at the end of the day, that agent will be reduced. So it is very important that you understand what we mean by oxidizing or by reducing. And whenever there's something that you don't understand, whenever there's something that you're missing, please feel free to WhatsApp or question so that we can assist you, because at the end of the day, you need to make sure that you master these terms. You need to make sure that you understand what is happening exactly in these reactions. So what do we mean by reduce? What do we mean by oxidize? The word reduce is just that there's a decrease in oxidation number, and oxidized meaning that there's an increase in oxidation number. So when I'm saying you are being reduced, just like the example that I was doing, it means now magnesium, because its oxidation number increases, it means magnesium is being oxidized. Why? Because it has undergone oxidation. But magnesium, if it is reacting with this kind of reaction of oxygen, it means it's going to be our reducing agent. Now, what happens to oxygen? Oxygen oxidation number decreased. So oxygen is going to be our oxidizing agent, first of all, because it will undergo reduction. And oxygen will be what? Will be reduced. Why? Because its oxidation number decreased from 0 to 2 minus. Therefore, it means it is an oxidizing agent and it is being reduced. So how do you identify the two? You will just look at the reaction, especially on the overall reaction, and check whether the agent, its oxidation number was increased or decreased. And if the oxidation number was increased, it means it has undergone oxidation, and you will end up concluding that that agent is being oxidized. If the oxidation number was decreased, it means it has undergone reduction reaction and it is being reduced. Okay. Now, the electrodes. Remember, as I said, that we are going to deal with electron transfer. So we need to have those substances that transfer electrons where they are lost to the site where they are gained. So we are going to use our electrode. And you need to know that electrodes must be solid, which are electric conductors. The first requirement for a substance to become an electrode, it must be a solid, and it must also be able to conduct electricity, because remember, it will be conducting what? It will be conducting electrons. So our electrodes, the word electrode come from electron. Our electrodes are going to conduct our electrons. And we know that they are going to conduct electrons from the site where they are lost to the site where they are gained. Now, in terms of the definitions, we said the process where electrons are lost is oxidation. So it means the electrodes will have the electrodes at the oxidation site, will have the electrode at the reduction site. The one that is found at the oxidation site is going to be called an anode. And we can use the word oxide just to remember which electrode we will find where electrons are lost. And then we'll have the next one, which is the cathode, which will be found at the reduction site where electrons are gained. Then we can use the word red cat just to remember that at the reduction site we have a cathode. So it is very important to know that, first of all, the electrodes must be solids and must be good conductors of electricity, so that they can transfer electrons from one side of the half of the cell to the other side, because we have two half cells for this reaction. Now, in conclusion, to try and summarize what I've just talked about in terms of the reduction, in terms of the oxidation, in terms of which anode, which electrode is found where, and what happens to the oxidizing and the reducing agent. So I said at the electrode where we have an anode, there will be a reducing agent that will undergo oxidation reaction, and that agent will be oxidized. And then when we find the cathode, there will be an oxidizing agent that will undergo reduction agent reaction, and that agent will be reduced. So already you know that at the cathode you'll find a oxidizing agent, and what type of reaction will occur is a reduction reaction. And what will happen to the agent? It will be reduced. Remember, what is being reduced is the agent by gaining electrons. What is being oxidized is the agent by losing electrons. So already when you see one agent in terms of the oxidation number, so we can say also here oxidation number, just to oxidation number, just to add, increases, oxidation number of an agent increases, and here we can say oxidation number decreases. Just to beef up our summary so that you know exactly what is happening in each half cell. Then the next thing that we're going to look at is the electrolyte. The electrolyte is a substance that contains the aqueous solution that contains ions and that also conduct electricity. So it's a substance of which aqueous solution contains ions, or it's a substance that dissolves in water to give a solution that conducts electricity. So it means there are some of the substances that cannot qualify, or solutions that cannot qualify to become electrolytes, e.g. like sugar solution. Sugar solution doesn't contain ions that can conduct electricity, therefore it cannot qualify to be an electrolyte. So for any substance to qualify to be an electrolyte, it needs to have ions which are positive and ions which are negative that can dissolve in water to conduct electricity. So we need not to confuse the word electrode and electrolyte. Electrode, we know, is a solid and it must conduct electrons. However, electrolyte is the solution that has ions that can conduct electricity. Now, how do we identify a galvanic cell? We identify a galvanic cell by using two electrolytes. And it is separated by a salt bridge, and there is a connection of galvanometer or voltmeter via an external circuit. And as I explained to say, in an external circuit, that is where we have a wire that will allow the movement of electrons. And we also have an internal circuit, which is our salt bridge, that will allow. So what will be moving inside the salt bridge is the ions, and it's our internal circuit. And what will be moving here is the electrons at our external circuit. The salt bridge consists of a salt solution which allows the movement of ions between two half cells. So the salt bridge will definitely allow the movement of ions. That is why we are using a salt, and we know that all our salts are having both positive and negative ions. Now, an anode in a galvanic cell will become a negative electrode, and a cathode will become a positive electrode. This is thoroughly explained when you see the reactions that happen in each half cell, so that you know that why in a galvanic cell an anode becomes negative and a cathode becomes positive. So it is thoroughly explained in terms of the movement of ions and electrons for these two electrodes to gain these charges of positive and negative. Remember, I'm saying it will become a negative electrode and the other one will become a positive electrode. The reason why they will become is because there's no connection of a positive and a negative terminal in a voltaic in a voltmeter reading, or in a voltmeter or in a galvanometer. So you need to understand that you cannot say you are going to connect an anode at the positive or at the negative terminal, because the galvanometer or the voltmeter doesn't have a negative and a positive terminal. Then, how are we now going to identify our half reactions? How are we going to identify which reactions undergo oxidation, which reactions undergo reduction? We are going to use our standard reduction potential table to assist us to choose the reactions, and also to assist us to say which reaction will undergo oxidation and which reaction will undergo reduction. When you look at the galvanic cell potential, what is the standard reduction potential, you will see there are two sides. The one side is divided, is separated also with a double arrow. Now, all what you read from this side are your oxidizing agents. Why am I saying are the oxidizing agents? You will see that everything that is this side is gaining electrons, and what you see this side is your reducing agent. So therefore, if you are given an overall reaction, or if you are given two half cells or half reactions, you will definitely know which one will have which one will undergo oxidation, which one will undergo reduction. How do you choose it? You can also use the cell potential to assist you to say a cell with a smallest cell potential will definitely undergo oxidation reaction because it will have a stronger reducing agent. When you look at your table, when you go up like this, it say is the increase, it's written increase in reducing strength or increase in reducing ability. And this one, it's having an arrow going down that say increase in oxidizing ability. Now let me take the first example, which is my lithium half cell, this one. when you look at lithium half cell, is the one that is having the most, actually is the one that is having the lowest. Let me just erase all. Is the one that is having the lowest cell potential, lithium, minus 3,05, as you compare to all the other half cells. So it means the reducing ability of lithium is the strongest as compared to all the others that will follow after. So lithium is the strongest reducing agent. Now, if lithium is the strongest reducing agent, remember this half reaction is having both the reducing agent and the oxidizing. Therefore, it means lithium ion will be the weakest oxidizing agent. So if you are a strongest reducing agent, your oxidizing agent will be weakest. And after identifying that you are a strongest reducing agent, it means you are the one that will undergo oxidation, meaning that lithium as a metal will lose more than any other reducing agent in this table because it's the strongest. But now, because we said this site is the one which represented our oxidizing agent, it means lithium ion will be the last to gain electrons because it's the weakest oxidizing agent. As we understand that the oxidizing agent is the agent that gains electrons and the reducing agent is the one that loses electrons. Therefore, you will firstly check which one is the strongest reducing agent and immediately identify it as the one that will undergo oxidation. Let me take barium. Let me take barium and zinc. So the first thing that you're going to check is barium and zinc as your reducing agent. So you can compare between barium and zinc, which one is the stronger reducing agent. So as I said, we're going to use our cell potential minus 2,90 and minus 0,76. Obviously, this one is having a greater cell potential as compared to this one. Therefore, because of the greater potential, it means barium will undergo oxidation. It's a stronger reducing agent than zinc. Therefore, because it's a stronger reducing agent than zinc, it means when coming to, because both of them, they can lose electrons, both of them are metals, but the other one can lose faster than the other one. Therefore, it means barium will undergo oxidation faster than zinc. Therefore, if you want to check whether you can, maybe if you want to protect zinc from rusting, it means you can cover it with barium because barium will undergo oxidation and protect zinc in undergoing oxidation first. Therefore, how do we write these reactions? When we write oxidation, we will start from the side of the reducing agent to the side of the oxidizing agent. So we can use a method like C method, and we'll say barium will undergo, which is going to be our solid, will undergo oxidation and form barium as it appears on the table, 2 plus 2 electrons, and zinc. Now, because zinc now is failed to undergo oxidation before barium, therefore it means zinc ion will gain those electrons that are coming. Remember, if it's an ion, it's in aqueous solution, plus 2 electrons that are coming from barium to form what? To form our zinc solid. So already we have identified our oxidation and our reduction half reactions. Therefore, after identifying the oxidation and reduction half reactions, then we can be able now to go further and say, do we have to write the overall reactions? Yes, we can write the overall reactions. As barium is giving zinc 2, zinc is accepting those 2. So we can, overall, we can now write one cell. What is exactly happening between barium and zinc? It means barium, which is our solid, will lose electrons, and those electrons will be accepted by zinc ion, which is our aqueous. And therefore, on the other side, the barium, after losing, it becomes barium 2 plus aqueous, and zinc ion, after gaining, it will become our zinc solid. So let's look at the oxidation number. It means barium moved from 0 to 2 plus, and zinc moved from 2 plus to 0. So we can immediately see that between zinc and barium, because these are our agents, we can identify which agent is oxidizing and which agent is reducing. So because this one is oxidation number increased, it means barium is our reducing agent because it undergoes oxidation and its oxidation number increase, and zinc 2 plus is our oxidizing agent because it has gained electron and its oxidation number has decreased. So already we have identified our oxidation and reduction between the 2 half cells, and we have already written the overall, which is 1 cell now, because half and half give 1. So we have already written a 1 cell, which is our galvanic cell for zinc and barium, and we also identify the reducing and the oxidizing agent. So we know that our table will go up to the level where there is hydrogen, which is our middle electrode, which is 0.0, which separates the negatives and the positives. So immediately when you go down, you know that the number of the potential, the cell potential increases. And this is because we are using the table 4b. That is where when from top to bottom, the cell potential decreases. There is nothing different when coming to 4b and 4a. It's just that the other one is looking upside down. Now, this is an example of a copper zinc cell, which is the same definition or the same explanation that I was using for barium and zinc. So if you look at zinc and copper, you will notice that the copper that we are using is the copper that comes from the copper 2 plus and the copper this one, where is having the copper solid and the copper this one. This is the copper that we are using most of the time. So when we have a zinc and copper, you can see here there is no zinc. It means the zinc half cell is at the top. So where is zinc half cell? This is the one that we have just identified. So already by looking at their cell potential, you will see that zinc will undergo oxidation and copper will undergo reduction because the copper half cell. Let me not say copper because copper definitely will not undergo reduction because copper as a metal cannot gain electrons, but copper ion or copper in an aqueous solution can be able to gain those electrons. Therefore, you will just choose the 2 half cells and identify your oxidation and reduction. Then after identifying, you can see that now your zinc become your negative electrode and your copper become positive electrode. What makes the zinc to become a positive, a negative electrode, is because inside the zinc sulfate solutions, there are zinc ions and there are also sulfate ions. Let me make them neutral because it's a neutral electrolyte. So after having a neutral electrolyte like zinc sulfate, and this side we have copper 2 plus. I hope the color is clear because this color is blue, and copper 2 plus and sulfate ions inside this electron. These are its negative. These ions are the ones that are inside our electrolyte. Now, what happens exactly when the cell starts to operate? When the cell starts to operate, because zinc is a stronger reducing agent than copper, it means zinc will lose electrons faster than copper, meaning that zinc will start losing electrons. How many electrons? 2 electrons, and these electrons will flow to the side of the copper. And as zinc loses these electrons, the electrons are also remaining on the zinc electrode as it is losing them, and makes this zinc electrode to become negative. So the reason why zinc become negative is because of the electrons that are being lost because of oxidation by zinc. And the zinc electrode will do what? Will now start to dissolve into the zinc sulfate solution. And as it dissolves, what will it produce? It will produce zinc 2 plus ions. So you can see now that on the zinc sulfate solution, we have now more of the zinc ions. And because the zinc ions are positive, it will make this side to be more positive. It will make the side of the zinc electrode to be more positive. And if the side of the zinc is more positive, it means now there is an imbalance in our electrolyte. It is no longer neutral as it started to be, as we started. It is now an imbalance. So this side is more positive because of the ions of zinc coming, and we will end up saying the concentration of zinc 2 plus ions increases. And if the concentration of zinc 2 plus ions increases, what happens to the zinc electrode? The zinc electrode mass will start to decrease. Why is it decreasing? Because the zinc is becoming smaller and smaller as it is dissolving into the zinc sulfate solution. making the zinc sulfate solution to be more positive, because what is happening is that more positive ions are coming to the solution, whereas the negative ions are remaining as they were in the beginning. As the electrons are reaching the site where there is a copper electrode, which is our cathode, the electrons will definitely remain on the electrode, because copper, remember, is the metal. And one of the properties of metals is that they lose electrons. So copper will also not be able to gain the electrons that are coming from zinc. But what will copper do? Copper will be able to transfer those electrons until they reach what? Until they reach the copper sulfate electrolyte. Then inside the electrolyte, remember, we have positive copper ions. So the positive copper ions will be happy to gain or to be attracted to the negative electrons that are coming from zinc. And immediately when they are accepting those electrons, they are now starting to become what? To become copper. And where will that copper be forming? It will be forming on top of the electrode of copper, making the mass of our cathode to increase. So the mass of the anode decreases and the mass of the cathode increases. And also, this side becomes more negative. Why? Because the copper ions are moving away from the solution, leaving the sulfate ions that are negative. So it means now the concentration of the Cu2 plus in the solution will start to decrease. So in this instant, we are having two ions that are now changing. The other ions are being forming as product, the other ions are being used as reactants. So when you look at the two half cells, you will see that on the zinc half cell, it means the zinc, which is our solid, is changing and becoming zinc 2 plus, which is our aqueous now. It is changing and becoming. So the zinc 2 plus ions are our product ions because they are formed during the oxidation. And the copper 2 plus ions, so copper 2 plus ions from the copper sulfate will gain the electrons from zinc and form what? Copper. So the copper ions, they are now becoming our reactant ions because they're the ones that are definitely gaining electrons. So come on, think about it. You will see that the issue is about zinc and copper ions. So it means as the zinc ion is changing and zinc is changing and becoming zinc ion plus 2 electrons, those electrons from zinc will be gained by copper 2 plus ion to form copper. So if you write our overall reaction, it means now these two electrons definitely, it means zinc will undergo oxidation and loses electrons, and those electrons will be gained by copper aqueous, which is our copper ions. And zinc, after losing, it becomes zinc 2 plus ion. And copper ions, after gaining, they become copper solid. So remember, these are our agents. These are our reactants. Now we need to see between zinc and copper 2 plus, which one is being reduced, which one is being oxidized, or which one is oxidation number is increased, or which one is oxidation number is increased. So zinc move from 0 to 2 plus, and copper 2 plus move from 2 plus to 0, meaning that now zinc become our reducing agent because it means it is being oxidized, and copper 2 plus become our oxidizing agent because it's being reduced. Now this is our agents that are reacting. Now in terms of the ions, we can see there are ions here and there are ions here. These are the ions on the side of the reactants, and these are the ions on the side of the product. So we are saying what will happen to the two ions when the cell is in operation. I think we have seen that the concentration of the zinc ions was increasing and the concentration of the copper ion was decreasing. And what do we refer to as zinc ions? We refer to zinc ions as product ions because they are the ones that are formed when zinc loses electrons. And this one are the reactant ions because they are the ones that gain the electrons as they are being lost by zinc. Therefore, we will say as the cell start to operate, the V cell, okay, let me just say V cell will start to decrease. Why does it decrease? As the concentration of the In this case, our zinc ion, which is our product ions, increases, and the concentration of reactant ions decreases. So that is exactly what makes the V cell to decrease. So it means for us to increase the potential or the cell potential, it means we must increase the reactant ions. It means we must increase the concentration of the Cu2 plus, because they're the ones that are being used up. So if the concentration of the Cu2 plus or the reactant ions is being used up, it means the cell will stop to function, because it means one of the reactant will be a limiting reactant, will be used up, and therefore the reaction will stop. And at the end of the day, we'll say we need to beef up, or we need to increase the concentration of the. So you don't need the zinc 2 plus ions, because definitely they will be formed. But what you need is the reactant ion. So the V cell will decrease as the product ion increase and the reactant ion, until the cell reaches equilibrium, and we say the V cell is now 0. That is exactly what happened to this cell when it's in operation. V cell is in equilibrium, and the cell is what is it? The V cell is equals to, let me just, is equals to V 0 volts, and then we know that now our battery is flat. Now, this is the explanation that I was doing. I don't think there's a need for us to repeat it, but it explains exactly what is happening in each half cell in terms of the increasing of the what is it? The increasing of the product ion, the decreasing of the reactant ion, until the equilibrium is reached, where we say our cell is 0. Now, what happens to the Soul bridge immediately when this happens? Now, because our half cells are now no longer in the they are no longer in the condition, or in the standard condition that we expected them to be, then the Soul bridge will try and neutralize the electrolyte by looking at what is happening. So it means now, let's say we are having our Soul bridge, which is potassium nitrate. So we know that we have K plus ion and NO plus ion. Now, the cation ions and the N ions will be part of our Soul bridge, which is our electrolyte. Cation ions are positive, N ions are negative. So after the Soul bridge, after seeing that the two electrolytes are now not neutral anymore because of the production of the zinc 2 plus ion and the reduction of the copper 2 plus ion, then it means now they will start and try to neutralize the two cells. They will send the N ions to the side which is more positive, and the cation ions to the side which is more negative. So normally the examiner will ask, where will the N ions go? Where will the cation ions go? The N ions will go to the anode side, and the cation ions will go to the cathode side. So that is why we say at the end of the day, the Soul bridge will also maintain cell neutrality. That is why this is one of the function of the Soul bridge. This is also explaining what, so the function of the Soul bridge, as I was saying, is to complete the circuit by connecting the two electrolytes and allow the ions to flow through without allowing the different solution to mix, and to maintain the electrical neutrality of the electrolytes of the half cell, the way I was just showing it currently. Now, this is already what I was explaining, to say when will the V cell reaches 0, which we call equilibrium, is because of the decrease in the reactant ions, and the increase in the product ions, and the decrease in the reactant ions. And already we have talked about how do we write half cells. We know we start with the side which is oxidation, and we end with the reduction, making sure that the oxidation start with our reducing agent and our reduction start with our oxidizing agent. Okay, this is an example of a half cell. And then in a case whereby now you find that a reducing agent is losing electrons that are more or that are less than the ones that are required by the oxidizing agent, we need to balance our equation. Like in this case, when we have an aluminum half cell and a silver half cell, you can see that aluminum is producing 3, whereas silver needs only 1. So it means we need 3 of the silver to gain the 3 electrons from aluminum. Therefore, we normally balance our equations when we are definitely writing our overall cell reaction. Therefore, we always multiply the number of electrons of the other cell. So it means with this one, we'll multiply the half cell of aluminum with 1 and the half cell of silver with 3, so that we balance our equation. And then at the end of the day, this is going to be our overall net cell reaction that is balanced, so that we know that for each aluminum, it means it must give 3 silver ions, these electrons, so that our reactions can be balanced. And we know that already, because this one is oxidation number changes, is our reducing agent, and our silver ion is our oxidizing agent. Make sure that always when you write the agents, you look at the side where they are reactants, because they're the ones that are providing the agent. Now, the cell notation, I normally say the cell notation, we write it as ABC, whereby we will start writing from the anode side, and then the salt bridge, and then we go to the cathode side. After explaining the cell notation, we'll just take a little break so that we just breathe a little. So how do you write it? You'll write from the anode side, which is the oxidation process, to the cathode side, which is the reduction process, and making sure that always you have your solids at the end. So your solids will be your edges, meaning that you'll start with a solid and end with a solid. In cases where you don't have a solid, definitely you need to provide that solid. And how do you provide the solid? As I explained, we're going to provide our inert electrodes that are non-reactive in those reactions, so that they act as solid, because they must be electric conductors. They must allow electrons to move from the side of oxidation to the side of reduction. So in case where you don't have these electrodes, the cathode and the anode, you need to provide them, because they are definitely needed. Like when we look at the example, let me just use the example that we just did now. In this case, we have aluminum, we have silver. So we are having the electrodes. So how do you write it? We know that aluminum changes and become aluminum 3 plus. Silver ion changes, become silver. So the anode is our aluminum, which is our solid. And then phase boundary, our aluminum ion, which is our aqueous. So we are done with the site of oxidation, and then salt bridge, and then our silver ion, which is our oxidizing agent, and then phase boundary, our silver, which is our solid. So this is the cell notation. This side is the side of the anode, this is our salt bridge, and this is the side of the cathode. And you can see that all my solids are at the end, and all my aqueous are in the middle, just next to the bridge, just next to the river, because they are the solution, and the solutions are next to the bridge. Okay, this is an example of a cell notation where we are showing copper and zinc half cell, the one that we just discussed, to say obviously we'll start with our solid and end with our solid, and everything that is in the middle will be. So we are going, before we go to this question, we are going to just take a 2 minutes break, so that we breathe a little bit, and then after 2 minutes we'll come back and continue with our lesson. Welcome back, grade 12s. We are going to start and look at our activities and see how do we answer questions on this part of a galvanic cell. Now, with me, I'm having two half cells, the iron 3 plus to iron 2 plus half cell and the hydrogen half cell. Now, we are going to try and see whether we can be able to answer questions in terms of what we have just learned in a galvanic cell. So we are going to look at the two half cell. The first thing that we need to look at is which half cell between the two will undergo oxidation and which one will undergo reduction. So the only thing that will assist you definitely is going to be our table. So when we go back to our table, we're going to identify the two half cell and see which one will undergo oxidation and which one will undergo reduction. I hope you, when you in your case, you have the table with you, so you can quickly. So let me see. Okay, we have iron 3 plus and iron 2 plus. Let's just see here. Let me just try and clear everything. Okay, so let's now start and looking at our 12 cell. This is the first half cell that we are provided. Okay, let me just choose an ink. Is the iron 3 plus going to iron 2 plus, this one of 0.77. And then the other one is the hydrogen half cell, this one. So when you look at the cell potential, you can immediately see that hydrogen half cell is having a lower cell potential as compared to iron half cell. Therefore, it means hydrogen half cell will undergo oxidation and iron 3 plus half cell will undergo reduction. And already we know that oxidation is going to be H2 gas. In this case, we are provided a gas giving us 2H plus 2 electrons. This is our oxidation. And reduction, we write it as it appears, Fe3 plus aqueous, and then plus electron, giving us Fe2 plus aqueous. So that is the first thing that you have identified. That is the first thing that you know about the two half cells. Then let's go to the questions and see what is it that we need to do in terms of these two half cells. I'll just try and go up. Okay. Okay. Let me just go back. Fine. Now they say write down the oxidation and the reduction reactions for the two. So there is no order of the exam of the way the examiner will give you. The examiner sometimes can start with any reaction or whether it's reduction or oxidation. They're just providing the reactions. So don't think that always when iron is given first it will undergo oxidation and this one will undergo, because this is not a cell notation. It's just two reactions provided to you. So you need to figure out which one will undergo oxidation and which one will undergo reduction. Then we have already done that. We have seen that this one will undergo oxidation and the other one will undergo reduction. And then the next thing they say, identify the anode and the cathode. Now, what is it about anode and a cathode? Remember, we said the two electrodes. The electrode is the solid electric conductor. Now we're going to look at our two half cells and check whether which one is having an, or where is our solid conductors. When I look at the iron 3 plus, I'm having aqueous. Even this side, I'm having aqueous. This one is aqueous, this one is gas. So it means we don't have, for both of the reactions, we don't have our solid conductors. Therefore, in this case, we need to provide them. And I said in a galvanic cell, we normally provide our inert electrode as what? As platinum. So it means our cathode will be platinum and also our anode will be platinum. And we'll see that when we are definitely writing, we are writing our cell notation, because we need to represent them. They won't be part of our half reactions because they are inert, they are not reacting, but they will be part of our cell notation. The platinum will be part of our cell notation because that was built the entire cell. And then write the overall reaction. So because we have identified the hydrogen half cell as our oxidation, 2H plus 2 electrons, and the other one is going to be Fe3 plus, which is aqueous, plus an electron giving us Fe2 plus, which is also an aqueous. So you can see that the number of electrons that hydrogen gas is giving is not going to be sufficient for the ion 3 plus to accommodate them. Therefore, we need to balance our equation. So here is 1, here is 2. We are going to multiply this side with 1 and this side with 2. And when we multiply everything, it means now our electrons is going to be H2 gas. I'm going to write it again so that we all follow 2H plus after multiplying with the electrons. And then this one is going to be 2Fe3 plus, which is our aqueous, plus 2 electrons now because we have multiplied, giving us 2Fe2 plus, which is also aqueous. Therefore, the 2 electrons will cancel each other, and our overall now is going to be H2 gas. Let me write it here alone, which will lose electrons and give it to Fe3 plus aqueous. And then our H2 after losing becomes H2 plus, 2H plus, which is also aqueous because it's an ion, plus 2Fe2 plus, which is also another aqueous. So this is our overall reaction. Then the other question says, identify your oxidizing and your reducing agent. So always I said our agents, we identify them at the site of the reactants. So we'll just check. So hydrogen moved from 0 to 1. It means there was an increase. And then ion 3 plus moved from 3 plus to 2. It means there was a decrease. So our oxidizing agent, let me start with the reducing. Our reducing is going to be H2 gas. And our oxidizing is going to be Fe3 plus aqueous. That is our reducing and oxidizing agent. And then the cell notation. Now remember, on the cell notation, we need to know how do we assemble our cell if we want our cell to function. And in our case, remember, our cathode and our anode were both platinum. So it means we'll start and say platinum for our anode, which is a solid, and then phase boundary. And then we go to hydrogen gas, which is our reducing agent. And then phase boundary, we go to our hydrogen, which is our aqueous. And then salt bridge, we go to our ion 3 plus, which is our aqueous. Now remember, this is a phase boundary. If the phases are the same, we use a comma. So it's going to be Fe2 plus, which is also aqueous. And then phase boundary, and then platinum, which is our solid. So you can even see even here that our solid will still be at the end because they're the ones that are providing the surface for the two reactions to occur. So it means the electrons will move from the platinum this side and going to the platinum this side. That is our cell notation. So you will need to understand that you will only include your inert electrodes when you are writing a cell notation, but they are not included on the both half reactions, and they are also not included on the overall cell reaction. So these are the solutions that I was providing and also trying to make sure. Now we also need to calculate the EMF of the cell, which is the cell potential. Now what you need to understand is that these cells operate at the standard conditions. So the standard conditions for these cells are always provided as the temperature is going to be what? It's going to be 25 degrees Celsius for them to operate or function well. The concentration, it must be 1 mole per decimeter cubed. And then in case where there are gases, like the previous example that I made where there was hydrogen gas, you are going to use pressure as 101,3 kilopascals. The standard conditions are also provided on your exam guideline. Therefore, it is very important that you know which conditions are relevant for which type of a cell. Because if you are using only the solid and the aqueous solutions, then there's no need for you to include pressure. So you need to know when do you include pressure. Temperature can be applicable in everything. Concentration can be applicable in everything because we have electrolytes. But pressure, you must be very careful. For the previous example, yes, pressure can be applicable because we were having a gas, which was hydrogen. But with the ones that I did before, like this one, we'll only use what? We'll only use the temperature and the concentration because we don't have gases. So it is very important to know when are these conditions going to be suitable. So for us to calculate the EMF, we are going to use these formulas to calculate the EMF, which is E theta cell is equal to E theta cathode minus E theta anode, or we can say E theta cell is equals to E theta reduction, subtract E theta oxidation, or E theta cell is equals to E theta oxidizing agent. So you can see that already by looking at this reaction, at the cathode, we are going to have reduction reaction, and the agent that is going to undergo reduction reaction is going to be our oxidizing agent. At the anode, there will be oxidation, and the agent that will undergo oxidation is going to be our reducing agent. Therefore, after knowing these EMF calculations formulas, then you can be able to calculate EMF. Always know that at the beginning, the EMF is at its maximum. Immediately when the cell starts to function, the EMF will start to decrease until the cell reaches equilibrium where it says 0. And there's no need for you to abbreviate these formulas because they are provided to you on your data sheet. You copy directly as they appear on the data sheet. So these are the conditions that I just explained now, which are providing us, especially the concentration, can also be used in a form of calculations, because if you already know the concentration, you can find the number of moles, you can find the volume of a substance, because the concentration is provided to you for a galvanic cell. Now, where were the numbers that you saw in the table coming from? They were coming from this electrode called hydrogen, and it's referred to as a reference electrode. So it means all the numbers that you see on your standard reduction cell potential table, they were determined by connecting them with a hydrogen half cell, because it's the one that is 0,00. I think you have seen that the cell potential of hydrogen is 0,00 volts. So whatever that you connect with hydrogen, it will give a cell potential of each half cell that is part of the table. And we can see that platinum was also used here as the inert electrode to allow this hydrogen half cell to function with other half cells, because as the hydrogen half cell doesn't have any surface to react on, because it doesn't have an electrode, so they provided a platinum. Okay, now let's look at this following question. We have platinum, hydrogen, and then hydrogen plus. So this is the cell notation. I think it's the same as the one that we just did now. So the question says, which one of the following equations represent a cathode half cell? So the first thing you need to check which side is the side where we are going to find our cathode. And I said we are going to use A, B, C. So it means the cathode half cell is represented by this side. And then we can see that it's coming from Fe3 plus to Fe2 plus. So it means Fe3 plus was being reduced to Fe2 plus. So the correct answer for the first one is this one. This one is incorrect because it says Fe2 plus was being oxidized, and this one shows oxidation reaction. These two are automatically obviously wrong because they are on the side of the anode before the bridge. Then if you look at this one, nickel going to nickel plus, silver ion going to silver. Already this cell notation is telling us which one is our reducing agent, which one is our oxidizing agent, which side is oxidation, which side is reduction, and which electrode is anode, which electrode is cathode. So they're saying a bulb connected across the two electrodes glows brightly. After some time, the brightness of the bulb decreases. So what will decrease the brightness of the bulb? It means the V cell is also decreasing. So the brightness will always deal with the cell potential. If the cell potential decreases, it also means that the brightness of the bulb will decrease. Therefore, what makes the brightness of the bulb to decrease, or what makes the cell potential to decrease? They say the silver electrode is used up. We know that the silver electrode is very impossible for it to be used up, because actually it's our cathode that is not gaining electrons, that is not even dissolving to the solution. So there's no way that it can be used up. And they say nickel electrode is being used up. The nickel electrode, it is not easy for this electrode to be used up as a metal, even though it dissolves into the solution to form these nickel ions, but it will definitely not be used up. It will still remain. You know how difficult it is to get a metal to be used up. So definitely it is not. And then let's look at the ions. The ions are the ones that now will tell us what makes the V cell to decrease. So always when you refer to the V cell, check whether the ions are decreasing or increasing, because the V cell, as we explained, will increase or will decrease when the reactant ions are decreasing and the product ions are increasing. So in our case, these ones are our product ions, and the silver ions are our reactant ions. So we know that for the V cell to decrease, it means the silver ions must decrease because they are the reactant ions, and either the product ions must increase. So when you look at number C, the concentration of silver ions increases, which is correct. The concentration of nickel ions, no, definitely is incorrect. What must happen here is that for the V cell to decrease, the concentration here must increase. Therefore, the correct answer is number C. Then this one, we are provided with a galvanic cell because there's a salt bridge. There are two electrolytes. The diagram below represents a galvanic or voltaic cell functioning under standard conditions, which is very important, using silver and unknown metal M. So they didn't tell us what is another a metal of another half cell, but they provided us with the EMF of the cell, which is our voltmeter reading. So this number represents our EMF already because it's the one that is read by the voltmeter. And when you analyze the diagram, you can see that now they are showing us the movement of electrons. They are coming from the side of M, they are going to the side of silver. So immediately they are telling us which side undergoes oxidation, which side undergoes reduction. And we are having electrolyte of silver and the electrolyte of M, which we don't know, which we need to identify. So the first question says, which electrode is the cathode? So for the mere fact that the electrons are moving away and they're being repelled on the side of this, which makes it to be negative, and this one makes it to be positive. Therefore, we will see that our cathode is going to be our silver electrode, because that is where electrons will be accepted. That is the side where reduction will take place. The next question says, identify electrode M by performing the relevant calculations, 5 marks. So we need to say what is M after being provided with this V cell or the EMF. Therefore, we are going to use our equation that says E theta cell is equals to E theta cathode minus E theta anode. The examiner provided us with the E cell, which is 0.93 is equals to, the cathode is silver. So if you can go to the table, you see silver is 0.80 volts. So we'll just substitute 0.80 volts minus M. We don't know what is M. Therefore, we're going to say 0.93 minus 0.80 is equals to minus M. So our M, okay, let me say minus M is equals to 0.13 volts, which is going to be negative 0.13 volts. So after finding this cell potential, you can go back to your table and check what was represented by M. And you will find that M was represented by what? M was represented, let me just, M is what is PB is lead. Because when you go back to the table, you'll see that M definitely is lead after the calculation. So the 4 marks is for the calculation, and 1 mark is for you to say this was represented by M. And then the salt bridge is now filled with sugar solution. Obviously, this is not an electrolyte, and it cannot qualify to be a salt bridge. Therefore, they say what will the voltmeter reading be when the cell is in function? So it means now that our voltmeter reading will read what? 0 volts, because it means there won't be any movement of ions and electrons because our salt bridge is not functioning. Okay, this is just the solutions of the questions that we asked in our previous. Now let's look at this one. This one is having the oxygen and peroxide half cell, and also the copper and copper 2+ half cell. So they say which electrode is the cathode. So when you go to a table, definitely you'll see that when you go to a table, your oxygen will be below copper, or copper will have a low potential as compared to oxygen half cell. Therefore, you will identify your cathode as copper. But make sure that the substances or the spaces that you use, are the correct ones. Let me just go back to the table. Let's go back to the table and see between the copper and the, so that we know which half cell do we definitely choose. Where is the table? Okay, fine. When you look at the table, you will see now, let me just clear everything. Okay, so we are now looking at the oxygen, which the oxygen peroxide is this one. So check exactly what you need. And the copper to copper 2 plus is this one. So already you see that the copper is going to undergo oxidation and this one will undergo reduction. So if you write oxidation, you know we write it as C and reduction like this. So it means our copper will be Cu2 plus, Cu going to Cu2 plus 2 electrons. And this one is going to be our oxygen plus 2H plus 2 electrons, giving you hydrogen peroxide. So immediately when you look at this 12 cell, you can see that this one doesn't have any electrode. So what comes into your mind is that when I write the cell notation, I must include platinum here so that it can assist this electrode to function. So we are going to, let's look at the questions. We are now going to look at what happens to the two half cells when they undergo net cell or overall reaction, because the other one is provided. Okay, fine. All right. So already we have identified our cathode. So which one is going to be our cathode? Definitely, because copper has undergone a reduction, oxidation, it means our cathode is going to be what? It's going to be platinum, because this is the site where reduction will occur. And then write down the oxidation half cell. This one is the one of copper, forming copper 2 plus 2 electrons. And then reduction is the one that of oxygen plus 2H plus 2 electrons, as you copy it, giving you hydrogen peroxide. And then the balance net reaction, they give equally. So it's going to be copper plus oxygen plus 2H plus, giving you copper 2 plus H2O2. And then the cell notation now, remember, is copper, which is our solid, phase boundary, Cu2 plus, and then phase salt bridge, and then O2, which is a gas, phase boundary, 2H plus. Then this one is gonna be what? And then going to, because this one is a liquid, H2O2. So this is our cell notation. Remember, phase boundary, platinum, because the platinum was reacting as our surface for this half cell because it didn't have any surface. And then calculate the initial EMF. So we know that for copper we have 0.34, and for this half cell you'll just check for this one of the oxygen going to hydrogen peroxide to see the cell potential and calculate the EMF. So this is what we were saying. This is the half cell of reduction and the cell notation. And then the EMF is this one, whereby we find that this is 0.68 minus 0.34, which is 0.34. And the answer is positive, showing that this is a spontaneous reaction. And then this one says, the table below shows two half cells A and B used to assemble an electrolytic cell under standard condition. So we have two half cells, cell A and B. Cell A is having a copper half cell, cell B is having a silver half cell. So immediately when you look at the two cells, you'll see which one will undergo oxidation and which one will undergo reduction. State the energy conversion that takes place in this cell. Obviously, the energy conversion that takes place in this cell, because there are two electrolytes, you can see it's a galvanic cell. Therefore, it means it converts chemical energy to electrical energy. And then number 2 say calculate, this is very important, calculate the mass of zinc, of silver nitrate used to prepare 1.50 decimeter cube of electrolyte B. Now, how do we calculate mass? We know that for us to calculate mass, we're gonna say N is equals to M over M. But we are only provided with the volume. So how do we find N if we are provided with volume? We know that C is equals to N over V. Therefore, our volume is in cubic centimeter. We are going to divide it by 1,000 to find our volume in cubic decimeter. Therefore, remember the cell, they said it operates a standard condition. Already the examiner is giving us the concentration of this cell. What is the concentration? Obviously, the concentration will be 1, which is equals to N, and then the volume divided by 1,000 is going to be 0, I think 0.15 cubic decimeter, if I'm correct. Therefore, our N is going to be 0.15 mole. Then after finding the number of moles, then we can go and say the number of moles is going to be 0.15 or 0.015 equals to, then mass we don't know, but we find the molar mass of silver nitrate, and then we'll definitely go to the periodic table and find the molar mass of silver nitrate, which is going to be what we're going to include here and cross multiply and find our mass in grams, which is not gonna, it's what we're not gonna do now because we don't have enough time to do that. But what was the hiding information that the examiner was giving us for us to calculate is this weight standard condition that was providing us the concentration, which is 1 mole per decimeter cube, because this is the condition that these cells will operate on. Define the term reducing agent. We know that a reducing agent is an agent that will lose electrons, that will undergo oxidation, and that will be oxidized. And then name or formula of the reducing agent. Now, for you to identify the reducing agent, we need to know which one undergo oxidation. And we know that copper half cell will undergo oxidation. So our reducing agent is between copper and zinc. So it means our reducing agent in this case will be copper, because it's the one that will undergo oxidation faster than, not zinc, silver. So this one will undergo reduction. So silver will undergo reduction and copper half cell will undergo oxidation, which will make copper to become our reducing agent. And then the balance reaction that takes place. So it means you will have to write the two half cells. You need to write the copper going to copper 2 plus 2 electrons. You can indicate the phases. Aqueous, this one is solid. And then the silver ion, which is aqueous, gaining the electron and becoming silver. Therefore, we know that they don't balance, so it means this one will be multiplied by 2. To write the overall is going to be copper solid plus 2 Ag plus aqueous, giving us Cu2 plus aqueous plus Ag, or what is it, is 2 Ag solid. Therefore, this is our overall reaction according to the question, which is 3 marks. 1 mark for the site of the reactants, 1 mark for the product, and 1 mark for the balancing. And then calculate the initial EMF of this cell. So when we calculate the initial EMF, we know that we're going to use E theta cell, which is going to be E theta cathode, subtract E theta anode. Then we have already identified our silver half cell as our cathode, so it's going to be 0.880 subtract 0.34, and then we get our EMF for the cell, or E theta cell for this cell. Okay, let me just go back again. And then how will the EMF of the cell be affected if the concentration of copper ions increases? So now we write increase, decrease, or remain the same. Where did we get the information about the E cell or the cell potential? The cell potential, we said it will decrease when the concentration of the reactant ions decreases, and the concentration of the product ion increases. Now, the next thing that comes into mind is the EMF of the cell will be affected. How will it be affected by the copper ions being increased? Now let's go to our cell notation or our overall reaction. Because here we have written the overall reaction. Now there are two ions that are involved, is silver ions and copper ions. Now we check between silver ions and copper ions, which one are the reactant ions and which one are the product ions. So when you look at this, the silver ions are found on the side of the reactant. So these are the reactant ions. And the copper are the product ions. And we already know that the increase in the concentration of copper 2 plus, which our product ions, will make the V cell to decrease. Therefore, it means when we increase the copper 2 plus ions, we are definitely going to make our cell potential to decrease, because those ions are the product ions. They are not the ions that are going to accept the electrons. Therefore, the correct answer, it means our cell potential will decrease by increasing the ions of copper in reaction A. Now, as we look at the time, we can see that the time is not enough for us to deal more with an electrolytic cell, but we'll try by all means to just give a summary of few things on electrolytic cell and see whether we cannot complete it, as we are going to do our next topic in our following week, and just deal with the things that are very important on an electrolytic cell. We are just left with few minutes. Now, in electrolytic cell, we are also going to look at the definitions, and we are also going to look at the movement of ions and electrons. Now, they say describe the movement of ions in the solution and state the direction of electrons. So whatever that we did in a galvanic cell will definitely not change so much in an electrolytic cell, because all the processes that we did in a galvanic cell, they are still going to occur in an electrolytic cell, because we're going to talk about the movement of ions, the movement of electrons, their half reactions, and the overall cell reactions. But what is important is that now we are dealing with the cells now that are provided energy to operate. And we are also going to look at the 4 processes that are going to be undergone by the cells which are electrolytic. We are going to look at the decomposition of copper chloride, electroplating, refining of copper, and the electrolysis of concentrated sodium chloride solution in and they use in the chloroalkali industry. Now, the first thing that I can explain is that these are the cells now that converts electrical energy to chemical energy, and that doesn't make them to be opposite of what we just did, because we said galvanic are chemical to electrical. The only thing is that now we need electrical energy for these cells to operate. And we know that now, because energy is added, then these cells are going to be endothermic. So the rate of this cell reaction can only be increased by increasing the temperature, because the increase in temperature favors endothermic. If we decrease the temperature, if the cell, definitely the cell will favor the reverse reaction, which is going to be our exothermic. So they are non-spontaneous because they are endothermic. They use electrical energy to function. And then this is just an example of an electrolytic cell. What you can see is that now they have one electrolyte, unlike in a galvanic cell where we're having 2 electrolytes. So in an electrolytic cell, we're going to have one electrolyte, and both our electrodes will be dipped in the same electrolyte. Now, because in this case, we're going to have our cell, which is going to be our power source, it means one of the electrodes will be connected at the positive terminal and the other one at the negative terminal. So the electrode that is connected at the positive terminal will be our anode, and the electrode that will be connected at the negative terminal will be our cathode. So it might seem like it's an opposite of a galvanic cell, because in a galvanic cell, our negative electrode was our anode, our positive electrode was our cathode. The reason why that happened is because we never have any cell connectivity in a galvanic cell, so we need not to confuse the two. Now we are connecting our electrodes in a power source, and we are connecting our electrode in a power source, which is the direct current. Therefore, you need to know that electrons need to always flow in one direction, from the side of the anode, which is positive, to the side of the cathode, which is negative. Then, as I was saying, we are going to look at the movement of ions in an electrolyte. These are the ways that we used even in our previous cell, which is galvanic cell, and explain what is meant by electrolysis, which is the chemical process in which electrical energy is converted to chemical energy. And then the electrodes are still two, anode and cathode, and they will be connected in a cell. As I said, we are going to use direct current from our power source, which will make our reaction to be non-spontaneous. Therefore, before I go, so it means now what I'm going to do, because our time is up, as we are going to start with our next lesson, we are going to now look at different processes that will be undergone by different electrolytic cells. So we'll look at the 4 processes, which will not take so much time because we already know what we mean by oxidation and reduction. But making sure that always when we are dealing with the 2 cells, know that they are not opposite of each other, but they are functioning in a different way in terms of energy convention and in terms of the requirements as we are going to start the reaction. So for today, we have come to the end of our lesson. I hope this revision will assist you in answering any question on question 8 and 9. So we are just about to finish our question 9, which is what we are going to start with in our following lesson. But make sure that whatever that you have or that they are misunderstanding on a galvanic cell, please look back and check whether you are able to catch up on the things that we have missed in our previous lesson. From my side, I would like to say thank you so much for watching. Until next time, goodbye from me.